Hello, good afternoon. Here we are again for another lovely session of MENG 3310 Fluid Mechanics. This is a make-up lecture to make up for the lecture we would have on Friday, except for our senior day events, which will take place during the normally scheduled time for our class. Anyway, this will be the last video lecture in this series, at least for now, at least for this semester. I may edit these in the future and improve upon them as I see fit, but for now, this will be the last lecture for the spring 2017 semester here. Okay, so this is one final wrap-up lecture on drag and boundary layers, looking at some more of the concepts therein and a few more examples of calculating drag, lift, etc. All right, so let's consider this. Now, I have a few things I want to look at. First of all, let's take a look here, and it would help if I plugged in my tablet. That would help. Okay, there we go. And today we're going to be looking at a few concepts. So first of all, we're going to look at, I would actually like to clarify something on from the previous video. Clarification. So one quick clarification. When previously we looked at calculating the Reynolds number and drag coefficient for systems involving flat plates, fluids flowing past flat plates, etc. And there was a question of whether we used the relative or the absolute velocity for that kind of thing. And in this case, I can confirm that these are going to be calculated. The Reynolds number will be calculated via the relative velocity. Will be calculated via the relative velocity, or with the relative velocity. In other words, it all comes down to the all of our drag calculations, the coefficient of drag, the calculation of Reynolds number. All of this will come to it all comes to the speed of the fluid coming past or flowing past the plate or object. A fluid past object, or in relation to object. And we'll be using some of these concepts as well today. Or, well, actually, I recorded this on the same day as the previous one, but that's okay. Okay, so I want to review I have a few learning objectives today. I keep saying today, but for this lecture, I have a few learning objectives today. First, I wish to calculate the drag force on an object. Second, I wish to illustrate the method for determining the power needed to overcome drag. And finally, I wish to discuss fundamentally what produces lift on an object. So let us consider that. So let's look into this. Now, so let's look at estimating drag. So estimating drag. Let's look at estimating drag. Okay, and so drag is actually usually determined by pressure forces and less by shear. So drag is usually dominated by pressure forces. So usually dominated by pressure forces rather than shear. At least for most common everyday objects. And typically this needs to be determined experimentally. So for very simple objects such as a plate, we could actually calculate those via integration. And from base principles, for more complex objects, we need to use a prototype model. So we typically drag coefficients are determined experimentally. And you would set up such an experiment actually using the ideas of similitude that we discussed earlier in the course. So typically drag coefficients are measured experimentally using a prototype and model, either a full-size prototype or a scale model, using either a full-size prototype or a scale model. And however, for simple shapes, you can actually look up tables, and you can look up values of the drag coefficient in the table. So for simple shapes like a sphere, a cylinder, etc., you can look up a value for the drag coefficient in the table. For something like a simple shape, look up CD in the table. In a table, again, all of this is going to come back to our equation. FD is equal to, etc., etc. So FD is equal to 1/2 times CD. So again, the drag force, FD, is equal to 1/2 times CD, which is our drag coefficient, times rho U squared times A. Where, as I mentioned in the previous slide, U squared, or U here, is going to be the relative velocity between the fluid and the object that we're looking at. And what about this A? Well, A is going to be the cross-sectional area. Now or it's not the cross-sectional area, the characteristic area. Now for the plate, it was the flat area, but depending on your system, it could be different. It's a characteristic area. So I will discuss this a bit more following. And what I mean by characteristic area, it depends on what exactly the characteristic area is going to depend on what type of system you have. So consider a characteristic area here. It's going to depend on your type of system. So there are different options. For something like a plane or a train or something like that, well, maybe not a train, but definitely a plane, you would have the frontal area. The frontal area is really the what dominates things. So if you have a plane, if you look at the cross-sectional area, if you look at a plane from the front, you'll see something like this. You'll usually see, now there's some weird exceptions, but generally you'll see a cylindrical fuselage. So you'll see a circle like this from the front and a couple wings. The forward cross-sectional area, if you ever look at a plane from the front, you'll see that its cross-sectional area is actually very, very small. And that's because at the speed that planes travel at, they're going to have most of their drag forces are going to be produced via the frontal area. So most of these are going to be, so it doesn't really matter how long it is necessarily. It's primarily determined by the frontal cross-sectional area. And so planes obviously need to be as light as possible. They're something that when you have to lift your own weight instead of, say, just carrying it on the ground, weight becomes absolutely critical. So you need to minimize and also your drag becomes critical. So you absolutely need to minimize your drag force. And in this system, the drag force is dominated by the frontal area. Or in this case, again, example would be a plane. Another type of area would be a platform or a planform. So consider a planform, and that would be an example of this would be a boat, for example. So imagine you have a boat. So the reason in the case of an airplane that the cross-sectional area dominates, the forward cross-sectional area projection, the reason that dominates is because this is traveling at very high velocities. When you're traveling at hundreds of miles an hour, the frictional effects or the viscous effects are more minimal. And so what is really critical is the frontal inertial effects of the fluid striking the frontal surface of the plane. So for a platform, so for example, imagine a flat-bottom boat, like a river barge or something going down the Mississippi. In that kind of system, the velocities are relatively slow. The velocity of a barge going down the river is pretty slow. And so this is the shape of now this could actually be a flat-bottom boat, or it could be the projection of it. So if you imagine the hull of the boat, imagine the curved hull of a boat. If you were to trace out a flat shape from that, this would be the shape of the submerged portion if you look down. Of the submerged portion if you look down or looking down. So water tends to have fairly high amounts of surface tension and friction, etc. So, and especially if something is going relatively low velocity, the frictional forces can dominate more than the inertial forces from the front of the shape. So this would be more looking down. But whichever so the key here is that one of these is going to be critical, or possibly a combination of both of them. So you might be able to come up with a system where both of these are significant. In a plane, the frontal area dominates. In a something like a ship, the planform, the planar area dominates, but it really depends. And then, if I combine this together, I can have an expression for the power required to overcome this drag force. And the power is going to be the force of drag times V. So, the force of drag times V. We know that P equals FV, and we've seen that ever since basic physics. You saw that in high school physics. So P is the power to but this is it applied to drag. P is the power to overcome drag. V is going to be the velocity of the object relative to the stationary ground. Velocity of object relative to stationary ground. So this is the one case where you absolutely do have to use the absolute velocity rather than the relative velocity. In the absolute velocity that we mentioned previously, where we were talking about the velocity of the fluid relative to the object that is exerting forces on, in that case, that is where you're always going to want to use the U, the relative velocity. You use that for calculating your Reynolds number, you use that for calculating your drag force, Fd here. But once you actually have that to calculate the power required, you need to look at the absolute velocity V, or if we're talking a plane, this would be the ground speed of the aircraft rather than the airspeed. Okay. And where this comes from, again, if you think of this, work is useful energy. Work W or U is useful energy. So V relates to the useful work. So if you have a plane in a wind tunnel, it doesn't move. It isn't doing any work, but again, to actually do work, you need power to overcome that force, and you need power to do work. Okay, and to get the drag coefficients, again, as I mentioned, for very basic shapes, you can find many of them for you can find formulas and or just values for many common shapes, and you can go in your text and find many of these in chapter 9 of the Munson text. Next, so now I'd just like to work through a few examples of calculating drag, calculating power to overcome drag, etc. So let us consider this. First, I'm going to have a few examples. I'm just going to call the first one example 1. Example 1. So the first thing I'm going to consider is a flat movie screen, say like an outdoor theater. And let's say I wanted to design one of these. Well, whenever I'm designing a kind of structure or building that's going to have a large surface area relative to its strength, wind is absolutely going to be the critical design consideration for this type of system. So this is a movie screen, like one of those old outdoor movie screens. So it's a movie screen. And so it's projected up a certain height. And that's not going to be important, because now that would be important if this were a civil engineering class and I was asking us to calculate that. There are actual tools you can use, such as the ASCE7, to directly calculate or predict the maximum velocity that you'll have to design for based on height, based on even things of what's in the surrounding area, what area of the country, and different things like that. But we'll keep it very simple here, and I'll just give you the velocity. So here, let's say the depth of this is 20 feet, and the length of this is 70 feet, or the height of this is 20 feet, and the length is 70 feet. And then given the following, let's say given wind speed, if the wind speed equals 50 miles per hour, or, which is also doing a quick conversion, 73.33 feet per second, find the drag force. Find FD. Find FD. Now, this is one of those problems that we're not going to have to worry about the difference between relative and absolute velocity, because our object is stationary. So solution. Here, Well, actually, I could carry this a bit forward if I wanted to. I could actually say, if I asked us the power required for this sign to overcome the force of drag, well, in this case, it would just be 0, because this thing isn't moving. So it's u, it's v. Its absolute velocity is actually 0. So we could throw this problem directly into our power formula, and because the sign isn't moving, it wouldn't require any power to overcome the drag force. It does. And that, of course, makes intuitive sense. A stationary billboard does not need an engine attached to it in order to overcome the force of drag from wind applied to it. It just has to have enough internal support to resist those forces. So the drag force here is going to be equal to 1/2 times CD times rho times u squared times A. In this case, the characteristic area, since the wind is going into the screen, it's hitting it here. This is going to be, now, obviously the wind could come from any direction, but if this is a very thin screen, the wind that would be coming from the left here would be very minimal, and it wouldn't actually catch most area. If the wind was fixed coming from the left, then the drag would actually dominate. But the overall, in terms of the overall design, what's obviously going to control is the wind going into the page on this drawing here. So let's look at this. Now, if you turn to your text and look at an appropriate table, we can find the CD. There's a based off of the L over D. For a rectangle, you can find that the drag coefficient, it can be based off the L over D, and this is going to be equal to 3.0 in this case. And then you can extrapolate from this that the drag coefficient would be approximately 1.3. The drag coefficient would be approximately 1.3. And so then we'd also need the area, and the area is fairly simple. It's just 20 feet by 60 feet, and that would be 1,200 square foot, 1,200 square foot. And so then the FD is going to be 1/2 times 1.3, our drag coefficient, times 2.38 times 10 to the negative 3 slugs per cubic feet, that is the density of air. Obviously that varies, but we can just go ahead and use that value. Slugs per cubic feet times a speed of 73.33 feet per second squared times 1,200 square feet. And this is going to equal actually a quite large force of 9,983 pounds. This is quite a large amount of force. 9,983 pounds. So we can see that this is this is a pretty strong wind. It is a 50-mile-an-hour wind, but still, we can see that the forces generated against this screen are enormously large. This is the weight of multiple decently sized automobiles. That weight applied as a force, and it would be applied probably at the centroid. Well, actually, not exactly, but again, we don't want to get too much into the details of wind calculation, but that's okay. Okay. So let us say another one. Let's look at a different one. Let us say that a boat is towing a log. In example 2, a boat will be towing a log. In example 2, a boat will be towing a log. So given, again, boat towing a log, this log is going to be a cylinder. Big old log, big old tree trunk, 2 meters in diameter, so absolutely massive tree. 2 meters in diameter, and it will be 8 meters long. And it has the relative velocity between the water and the log, the u. We're given the relative velocity here, u will be 4 meters per second. And estimate. So all this is given, and then find the power required to overcome drag. Now, since we're not given anything about the speed of the water, I'm going to assume that the water is stationary. Like this would be something like a lake, that kind of thing. But if it were not, then if it were a boat towing the log down a river, then we would need to take that into account and either subtract or add to the relative velocity accordingly. So power required to overcome drag. So again, well, one thing I'm going to do first of all is I'm going to assume the entire log is submerged, which is obviously is completely impossible. It's not going to be totally submerged, but I'm going to assume it is pretty close to being submerged. And this is actually going to be kind of a conservative solution. This is a conservative estimate. So the more of the log that is out of the water, the lower the drag force, the lower the amount of power required. So if we just go ahead and assume the entire log is submerged, this will be a very conservative assumption. So I can look up in the book, and I found a table relating to a circular rod moving parallel to flow, and that's how I'm going to get my drag coefficient. Again, that's found in chapter 9. From a previous version of the book, it was figure 9.29, but that might not be appropriate for the current version of the book. Anyway, so again, the first thing I'm going to do is assume log is submerged. So that's the first step, assume the log is submerged. Then I go and say, okay, my L over D, it's in the table, it instructs you to calculate the ratio of the length to diameter, and in our case this is 4.0, and that leads to a drag coefficient of approximately 0.85. And the characteristic area in this case is going to be the cross-sectional area of the log, and so this is going to mean that the area is pi over 4 times diameter squared. So it's because this thing is moving like this, so here's the log, it's being towed along like this with the water kind of like there. So the frontal area that's being struck is this one here. So pi over 4 times 2 meter quantity squared, and that will equal 3.14 square meters. So exactly pi square meters of log will be striking the fluid. And so next I'm going to find the drag force, and this is going to be 1/2 times 0.85. Actually, let me do that on the next page. I think I want to keep that together with my power calculation. So find FD, drag force, and this is going to be that FD equals 1/2 times 0.85 times, let's go ahead and use the density for water of 999 kilograms per cubic meter, times 4 meters per second quantity squared, times 3.14 square meters. And this will produce a drag force of 21,341 newtons. Then if I wish to find the power required to do this, this would be P equals Fd times V, so the force of drag times the velocity, just a basic physics equation. That is 21,341 newtons times a velocity of 4 meters per second, and this will come to a value 85,400 watts, or more commonly a 85.4 kilowatts. And we could also convert that to horsepower if you wanted, but we have this in metric, so we're given this metric, so I'm just going to keep it in metric as well. So 85.4 kilowatts. So quite a bit of energy just to overcome the drag force of pulling this log along. And that is a continuous amount of power. So this really illustrates the idea of, illustrate the idea of the importance of drag forces. So for example, if you think of the energy required to take a car down a road, yes, it does take quite a bit of energy to accelerate the car, but once you're actually up and if you're accelerating onto a highway on a entrance ramp, it does take quite a bit of energy from the engine to accelerate you up to cruising speed. But beyond that, that's something you usually only have to do once, and then you lose that energy if you brake. But on a long trip, you only do that a couple times. But meanwhile, this drag force has to be exerted continuously. So the engine has to, this is the force, this is the power that the engine is going to have to continuously produce, or is going to have to continuously generate in order to keep the car moving at that kind of velocity. Or in this example, the amount of energy or the amount of power required to keep the log moving down the stream. Okay, so next I want to look at the final topic for this course, and that will be lift. So let us consider lift. And we're not going to work through a lot of examples with this, but I just want to discuss this in a general sense here. So let us consider lift. And these are going to be, by definition, a lift is a force normal to flow. It is a force normal to flow resulting from the pressure distribution, resulting from P distribution, resulting from a pressure distribution. So FL, the force of lift, well, the formula for this will be very similar to the drag. The formula will look very similar. 1/2 times CL, the coefficient of lift, times rho times U squared times A, where FL is the lift force and CL is the coefficient of lift. And so CL here is the lift coefficient, and it is a function of shape, just like drag coefficient is. This is the lift coefficient, and it is a function of shape. It is a function of shape. Okay, so next I'd like to look at some ideas of airfoils. What is an aerofoil? Well, an aerofoil, or an airfoil, it is the kind of thing you see, and it's the type of shape that characterizes, say, a wing on a plane. And it's characterized by two things. The aerofoils are shaped in order to produce wind, or to produce lift by two mechanisms. So they generate lift by two mechanisms. So the first one is going to be asymmetry. Asymmetry. And the second is going to be angle of attack. They generate lift through two different methods. Again, asymmetry is going to force velocity changes along the length, and that can affect pressure, etc. So if you have something like this, it's going to be asymmetric, and what common explanation you sometimes hear explained is that there'll be a longer length to travel along the top than the bottom. Longer means that there's lower pressure along the top than the bottom, which produces upward force. That's one way, that's one interpretation. So the curvature can generate the lift. The other is angle of attack. And some people, you hear people argue back and forth about which of these is more prominent, but really I think they both contribute to lift a great deal, in the sense that the way this works. So again, one way to think of this is with asymmetry is that a common explanation is that you have two different paths a particle could travel. It could travel the top, or it could travel the bottom, and the path, you design it such that you make the curvature such that the distance across the top is shorter than the distance along the bottom, or actually longer than on top than on the bottom. This means that the particle at the top will have to travel faster in order to keep volume conserved, and so then with higher velocities you'll get lower pressure, applying Bernoulli, etc., and then you'll get some lift generated there. It's a resulting force. Another bit more simple way to explain this is just a simple deflection kind of thing. If you have wind coming in here, a lot of it's going to be forced in order to get around the airfoil. A lot of it's going to have to be forced downward. So you're effectively just forcing wind downward, and the fact that you're forcing air downward means that you are forcing the wind upward. So the asymmetry, the way to explain airfoils through asymmetry, these are basically two different schools of thought. You'll see people explain airfoils by. The first one is this asymmetry, and it's based on pressure differences. The other is just a simple action-reaction kind of thing, and you tilt into the wind and it generates lift therein. But regardless, lift is still a reaction force. You obviously don't get lift unless you have fluid being deflected in a certain direction. So that is always key. That is always key to keep in mind, that lift is a reaction force. So lift is a reaction force. I want you to always keep that in mind, regardless of how you see it explained. So you can think of it in terms of high pressure or low pressure, or via deflected fluid. Can be explained by high pressure and low pressure, by high and low pressure. So you'd have low pressure above the wing and high pressure below the wing, or via simply forcing air to move downward. By high and low pressure zones, or by simply forcing air to travel below the wing, or deflecting them downward. Simply deflecting air downward, okay? And so again, the air, really both of these are in effect. So airflow, air follows the shape of the wing due to viscous effects or to no-slip boundary conditions. The shape of the wing due to no-slip boundary condition. And so again, you'll have a viscous force between the fluid and the surface, which causes it to travel at different velocities as the geometry requires. And of course, Newton airfoil pushes down on the air, which causes the plane to experience an upward force. Which means the plane is forced upward. Air pushes back against wing. And all of this is just Newton's third law. And so I think that's where we'll end it at. All of this, at the end of the day, just comes back to Newton's third law. As many of these things in this course do, we'll find that many of the things in fluid mechanics and the other areas of engineering can often come back to the very basics, ideas such as Newton's laws, etc. So Newton's third law wins again. And that would be a nice ending point. So I hope you've enjoyed watching these videos. If anyone actually watches the whole series, I hope you've enjoyed watching through these for my students this semester. I thank you for putting up with me recording these during class. I thank you for putting up with the technical errors a few times we've had along the way. But I hope you've learned a few things, and I hope you've enjoyed your time. So that'll do it for this semester. I may edit these videos further in the future and replace things as I see fit along the way. But I hope you've all enjoyed this, and as always, thank you.